Introduction to Schnorr signatures. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics, with a focus on networking. Also, hit the bell icon to get notified of new videos. Today we're diving deep into Schnorr signatures, which represent one of the most elegant and efficient digital signature schemes in modern cryptography. Named after German mathematician Klaus Schnorr, who invented them in the late 1980s, these signatures have gained significant prominence in recent years, particularly with their adoption in Bitcoin's Taproot upgrade in 2021. Unlike the more commonly known ECDSA signatures that were previously the standard in Bitcoin, Schnorr signatures offer several compelling advantages, including signature aggregation, smaller signature sizes, and proven security under standard cryptographic assumptions. What makes Schnorr signatures particularly interesting from both a theoretical and practical standpoint is their mathematical simplicity combined with their powerful properties. The signature scheme is based on the discrete logarithm problem, specifically the difficulty of computing a private key from a public key in elliptic curve cryptography. The elegance of Schnorr's design lies in its straightforward construction using basic modular arithmetic operations, yet it provides provable security that can be formally demonstrated through reduction to the discrete logarithm problem. This is quite different from ECDSA, which lacks such formal security proofs. Throughout this presentation, we will explore the full implementation details of Schnorr signatures, starting from the foundational mathematical principles and building up to actual working code. We will examine the elliptic curve operations that underpin the scheme, walk through the key generation process, understand the signature generation algorithm with its crucial nonce construction, and finally, implement the verification procedure. By the end, you will have a comprehensive understanding not just of how to use Schnorr signatures, but also why they work the way they do, the security properties they provide, and how they compare to alternative signature schemes. Mathematical foundations. Before we can implement Schnorr signatures, we need to establish a solid understanding of the mathematical primitives that form the foundation of this cryptographic scheme. At the heart of Schnorr signatures lies the discrete logarithm problem over elliptic curves, which provides the one-way function necessary for public key cryptography. An elliptic curve is defined by an equation of the form y squared equals x cubed plus a times x plus b, where the curve is defined over a finite field. In cryptographic applications, we typically work with curves over finite fields with a prime modulus, meaning all arithmetic operations are performed modulo a large prime number p. The elliptic curve forms a mathematical group under a point addition operation. This group has a special property called the generator point, often denoted as G, which is a point on the curve that can generate all other points through repeated addition. When we say a point P equals n times G, we mean adding the generator point to itself n times using the elliptic curve point addition formula. This operation is efficiently computable in one direction, meaning given n and G, we can quickly compute n times G. However, the inverse operation, given P and G to find n, is believed to be computationally intractable for properly chosen curves with large enough parameters. This asymmetry is precisely what makes elliptic curve cryptography secure. The order of the generator point G, denoted as n, is the smallest positive integer such that n times G equals the point at infinity, which serves as the identity element in the elliptic curve group. For cryptographic purposes, n must be a large prime number, typically on the order of 2 to the power of 256 for 256-bit security. The security of Schnorr signatures relies on the hardness of the discrete logarithm problem in this group, meaning that given a public key Q equal to D times G, where D is the private key, it should be computationally infeasible to recover D from Q and G alone, even though computing Q from D and G is trivial. In the Schnorr signature scheme, we also rely heavily on cryptographic hash functions, which must exhibit collision resistance, preimage resistance, and behave as random oracles in security proofs. The hash function takes arbitrary length input and produces a fixed length output, typically 256 bits for modern implementations. This hash function is used in the challenge generation step of the signature protocol, where it effectively transforms the signature protocol into a non-interactive proof through what's known as the Fiat-Shamir heuristic. Understanding these mathematical foundations is crucial because every step of the Schnorr signature algorithm, from key generation through signing and verification, directly relies on these elliptic curve properties and hash function characteristics. Elliptic curve parameters. To implement Schnorr signatures in practice, we need to choose specific elliptic curve parameters that define the mathematical structure we will be working with. The most widely used curve for Schnorr signatures, particularly in Bitcoin, is SECP-256K1. This curve was specified by the Standards for Efficient Cryptography Group and has become the de facto standard for many blockchain applications. The curve equation for SECP-256K1 is y squared equals x cubed plus 7, which is an unusually simple form where the coefficient a is 0 and b is 7. This simplicity actually provides some computational advantages in implementation. The field prime p for SECP-256K1 is a massive number, 2 to the power of 256 minus 2 to the power of 32 minus 977. This specific choice of prime was selected because it has a special form that allows for efficient modular reduction using the fast reduction algorithms. All coordinate arithmetic on the curve is performed modulo this prime, meaning after each addition or multiplication operation, we reduce the result modulo page. The size of this prime determines the size of the finite field over which the curve is defined and directly impacts the security level of the cryptographic operations. The generator point G is a specific point on the curve with coordinates that are standardized in the SECP-256K1 specification. The x-coordinate of G starts with the hexadecimal value 79BE667E and continues for a total of 64 hexadecimal digits, representing a 256-bit number. The y-coordinate similarly is a specific 256-bit value. What is crucial about this generator point is that it has a very large prime order, meaning the smallest positive integer n such that n times g equals the point at infinity is a prime number close to 2 to the power of 256. This order n is approximately 2 to the power of 256 minus a small value, and it defines the size of the subgroup generated by G. The security of Schnorr signatures on SECP-256K1 relies on the assumption that solving the discrete logarithm problem in the group generated by G is computationally infeasible. With the current state of cryptanalysis and available computing power, the 256-bit security level provided by SECP-256K1 is considered extremely secure, requiring roughly 2 to the power of 128 operations to break using the best-known algorithms like Pollard's row. This security level is far beyond what any conceivable computing system, including quantum computers with Grover's algorithm, could attack in any reasonable timeframe. The choice of these specific parameters represents years of cryptographic research and analysis to ensure there are no hidden weaknesses or backdoors in the curve structure. Schnorr signature structure. A Schnorr signature consists of two components, a scalar value s, and a point r. Though in practice, we typically only transmit the x-coordinate of r along with s, making the total signature size 64 bytes for SECP-256K1. This is one of the key advantages of Schnorr signatures over ECDSA, which requires 64 bytes for the signature pair r,s, plus an additional recovery byte in some implementations. The structure of a Schnorr signature is deeply tied to the proof protocol from which it derives, which we will explore in detail. The signature generation process begins with the signer selecting a random nonce k, which must be a uniformly random integer between 1 and n-1, where n is the order of the generator point. This nonce is absolutely critical to security. If the same nonce is ever used twice with different messages, an attacker can recover the private key through simple algebra. This is not a theoretical concern. but it has led to actual security breaches in various systems that implemented nonce generation incorrectly. For this reason, deterministic nonce generation following RFC 6979 is strongly recommended, where the nonce is derived deterministically from the private key and message using a pseudorandom function. The point R is computed as K times G, where G is the generator point. In the Bitcoin Schnorr signature scheme known as BIP 340, there's an important additional step where we ensure that R has an even Y coordinate. If the computed R has an odd Y coordinate, we negate K and use negative K instead. This convention allows us to save 32 bytes in the signature by only transmitting the X coordinate of R, since the verifier can reconstruct R knowing only its X coordinate and the fact that it has an even Y coordinate. This is possible because for any X coordinate on the curve, there are at most two corresponding Y coordinates, and they have opposite parity. The scalar S is computed using the formula S equals K plus E times D, where E is the challenge value derived by hashing R, the public key P, and the message M, and D is the private key. This formula is where the mathematical elegance of Schnorr signatures shines through. The challenge E binds the signature to the specific message and public key, preventing various attacks. The addition of K provides the randomness that makes each signature unique and prevents key recovery. The multiplication by the private key D is what proves knowledge of the private key without revealing it. The entire signature construction can be understood as a non-interactive zero-knowledge proof of knowledge of the discrete logarithm of the public key, transformed from an interactive protocol using the Fiat-Shamir heuristic. Key generation process. The key generation process for Schnorr signatures is straightforward, but must be implemented with extreme care regarding the source of randomness. The private key D is simply a random integer selected uniformly from the range of 1 to n-1, where n is the order of the generator point. This means we need approximately 256 bits of cryptographic quality random data. The randomness source is absolutely critical because if an attacker can predict or influence the private key generation, they can forge signatures or steal funds. For this reason, production implementations should always use cryptographically secure random number generators provided by the operating system or hardware security modules. In Python, we can generate cryptographic random numbers using the secrets module, which is designed specifically for generating random numbers suitable for security and cryptography. The secrets.randBelow function generates a cryptographically strong random integer in the range from 0 to n-1. However, we need to ensure our private key is not 0, so we typically generate the key in a loop until we get a non-zero value, or we generate in the range 1 to n-1 explicitly. Some implementations will also reject private keys that are extremely small or have other problematic properties, though this is typically more relevant for other cryptographic protocols. Once we have the private key D, computing the public key is simply a matter of elliptic curve scalar multiplication. The public key P is computed as D times G, where G is the generator point and times denotes scalar multiplication on the elliptic curve. This operation involves repeated point doubling and point addition operations, which are the fundamental operations in elliptic curve arithmetic. Most cryptographic libraries provide optimized implementations of scalar multiplication that use techniques like window methods or NAF representations to minimize the number of operations required. For a 256-bit scalar, a naive implementation would require 256 point doublings and approximately 128 point additions on average, but optimized implementations can reduce this significantly. The public key P is a point on the elliptic curve with both x and y coordinates, each being a 256-bit integer for sec P256K1. In uncompressed form, the public key would be 65 bytes, 1 byte prefix followed by 32 bytes for X and 32 bytes for Y. However, in the BIP 340 Schnorr signature scheme used by Bitcoin, we use a compressed representation where we only store the X coordinate. We also implicitly assume the y-coordinate as even, and if during key generation we end up with an odd y-coordinate, we negate the private key. This gives us a 32-byte public key representation, which is more space efficient and is part of what makes Schnorr signatures attractive for blockchain applications where every byte stored or transmitted has a cost. Nonce generation. The nonce key used in Schnorr signature generation is arguably the most security-critical component of the entire signature scheme. The word nonce stands for number used once, and this is a literal description. If you ever reuse the same nonce key to sign two different messages with the same private key, an attacker can algebraically solve for your private key using just the two signatures and messages. This is not a theoretical vulnerability, but it has led to numerous real-world security breaches, including the famous Sony PlayStation 3 signing key compromise where Sony's implementation used a static nonce. There are two main approaches to nonce generation. The first is random nonce generation, where for each signature, we generate a fresh, cryptographically secure random number between 1 and n-1. This approach is conceptually simple and was the original design for signature schemes like ECDSA and Schnorr. However, it places enormous trust in the random number generator. If the RNG is weak, predictable, or compromised, the entire signature scheme breaks. Furthermore, even with a good RNG, there is always the risk of implementation bugs that might cause nonce reuse in edge cases, such as when forking processes, duplicating state, or dealing with faulty hardware. The second approach, and the one strongly recommended for modern implementations, is deterministic nonce generation following RFC 6979. In this scheme, the nonce key is derived deterministically as a pseudorandom function of the private key and the message being signed. Specifically, we use HMAC-based key derivation with the private key as the key and the message hash as input. This means that for any given message and private key combination, we always generate the same nonce. This completely eliminates the risk of nonce reuse because the same message will always produce the same signature, and different messages will produce different nonces. The RFC 6979 derivation process works as follows. We first initialize an HMAC-DRBG, hash-based message authentication code deterministic random bit generator, with the private key and message hash. We then extract bits from this DRBG to form our nonce key. If the generated key is 0 or greater than or equal to n, we extract more bits and try again. This process is guaranteed to terminate quickly because the probability of hitting an invalid key is negligible. The security proof for RFC 6979 shows that as long as HMAC behaves as a pseudorandom function, which is a standard cryptographic assumption, the generated nonces are indistinguishable from truly random nonces to any computationally bounded attacker. For implementation, we will use SHA-256 as our hash function within HMAC, which is the standard choice for SEC-P256K1. Challenge generation. The challenge value EE is the component that binds the signature to the specific message being signed and the public key being used. In the original interactive Schnorr identification protocol, the verifier would choose a random challenge and send it to the prover. However, for a signature scheme, we need a non-interactive version where the signer can produce a signature that anyone can verify later without any interaction. This transformation from interactive to non-interactive is accomplished through the Fiat-Shamir heuristic, where the random challenge is replaced with the output of a cryptographic hash function. The challenge is computed by hashing together several components: the x-coordinate of the nonce point R, the x-coordinate of the public key P, and the message M. The specific format of this hash input is defined precisely in BIP 340 for Bitcoin Schnorr signatures. We concatenate these three values and hash them using a tagged hash construction. Tagged hashing is a technique where we prefix the hash input with a specific tag that identifies the context in which the hash is being used. For BIP 340, the tag is the ASCII string BIP0340/challenge. The purpose of tagging is to ensure domain separation so that hash outputs from Schnorr signature challenge generation cannot be confused with hash outputs from other contexts. The tagged hash construction works as follows. First, we compute the SHA-256 hash of the tag string itself. Then, we use this tag hash twice as a prefix before our actual data. Specifically, the tagged hash of data with tag T is computed as SHA-256 of the concatenation of SHA-256 of T, SHA-256 of T, and the data. This might seem redundant, but it provides strong domain separation and prevents length extension attacks. The output of the tagged hash is a 256-bit value, which we then interpret as an integer modulo n, where n is the order of the generator point. The security of the signature scheme critically depends on the collision resistance and pseudorandom properties of this hash function. If an attacker could find two different messages that produce the same challenge value when combined with the same R and public key, they could potentially forge signatures. Similarly, if the hash function's output were predictable or biased, it could weaken the security guarantees of the signature scheme. SHA-256 is chosen because it is a well-studied hash function with no known practical attacks against its collision resistance or preimage resistance properties, and it produces 256-bit outputs which match the security level of SECP256K1. The fact that the challenge incorporates R, the public key, and the message means that signatures are bound to all three components and cannot be reused or manipulated in various attack scenarios. Signature generation algorithm. Now we're ready to examine the complete signature generation algorithm in detail. The process takes as input the private key D, the message M to be signed, and produces as output a signature consisting of a 32-byte R component and a 32-byte S scalar. Let's walk through each step carefully, as getting any detail wrong can completely compromise security. Step 1 is to generate or derive the nonce K. Using RFC 6979 deterministic generation, we compute K as HMACDRBG with key equal to the private key D and input equal to the message hash. We must ensure that K is in the range 1 to n-1. If K equals 0 or is greater than or equal to n, we must reject it and generate a new candidate, though this should happen with negligible probability. Step 2 is to compute the nonce point R equal to K times G, where G is the curve generator. This point multiplication is typically the most computationally expensive operation in the signing process. Step 3 is where BIP 340 introduces an important optimization. We check if the y-coordinate of R is odd. If it is odd, we negate the nonce K to get negative K modulo n. This ensures that the final R has an even y-coordinate. The reason for this convention is that it allows us to save space in the signature by transmitting only the x-coordinate of R. The verifier can then reconstruct R, knowing only its x-coordinate and the fact that it has an even y-coordinate. This step is unique to BIP 340 and is not present in all Schnorr signature variants. Step 4 is to compute the challenge E as the tagged hash of the concatenation of the x-coordinate of R, the x-coordinate of the public key P, and the message M. The output of the hash is interpreted as an integer modulo n. Step 5 is to compute the signature scalar S using the formula S equals K plus E times D, all modulo n. This is the core equation of the Schnorr signature scheme. Let's understand what this equation means cryptographically. The term E times D is a product of the challenge and the private key. This is what proves knowledge of the private key. The term K is the nonce that provides randomness and prevents various attacks. By adding them modulo n, we get a scalar that simultaneously proves we know the private key D and that we generated a fresh random commitment R. The modular arithmetic ensures that S is always in the valid range from 0 to n-1. The final signature output consists of the x-coordinate of R, which we'll call Rx, and the scalar S. Both are 32-byte values, giving us a 64-byte signature total. This signature is then typically encoded in hexadecimal or base 64 for transmission or storage. The signature is valid for the specific message M and public key P used during generation. One beautiful property of Schnorr signatures is their linearity, which enables advanced cryptographic protocols like signature aggregation and threshold signatures, though we won't delve into those extensions in this presentation. The generated signature is deterministic when using RFC 6979, meaning signing the same message with the same key will always produce the identical signature, which can be useful for testing and debugging. Signature verification algorithm. The verification algorithm is the counterpart to signature generation and allows anyone with the public key to verify that a signature is valid for a given message. The verifier receives the signature components RX and S, the message M, and the public key P. The goal is to check whether this signature could have been produced by the holder of the private key corresponding to P. The beautiful aspect of Schnorr verification is that it's mathematically clean and efficient compared to alternatives like ECDSA. Step 1 of verification is to reconstruct the challenge EE. We do this by computing the same tagged hash that was used during signing, the tagged hash of RX, the X coordinate of P, and the message M. This gives us the challenge value that was used when the signature was created. It is crucial that the verifier uses exactly the same hash construction as the signer, including the tag and the order of inputs. Any deviation will cause valid signatures to fail verification. Step 2 is to reconstruct the nonce point R from its X coordinate Rx. Since we know from the BIP 340 convention that R must have an even Y coordinate, we can compute the Y coordinate from the curve equation and take the even solution. Specifically, we compute y squared equals x cubed plus 7, take the modular square root, and choose the even root. Step 3 is the core verification equation. We need to verify that S times G equals R plus E times P. Let's understand why this equation should hold for a valid signature. During signing, we computed S as K plus E times D modulo N. Therefore, S times G equals K times G plus E times D times G, which equals R plus E times P, since R was defined as K times G and P was defined as D times G. This is the fundamental equation that makes Schnorr signatures work. If the equation holds, we know the signature is valid. If it doesn't hold, the signature is invalid and must be rejected. In practice, we compute the left side as S times G and the right side as R plus E times P. Then, we check if they are equal as points on the elliptic curve. Point equality means that both the X and Y coordinates match. Some optimizations are possible here. For instance, we could rearrange the equation to S times G minus E times P equals R. Then, we would only verify that the X coordinate matches Rx. This saves us from having to reconstruct the full Y coordinate of R. However, for clarity in implementation, it is often clearer to implement the equation as stated. The verification algorithm is designed to be efficient. The most expensive operations are the two scalar multiplications. S times G and E times P. Modern elliptic curve libraries use techniques like Shamir's trick to compute the sum of two scalar multiplications more efficiently than computing them separately. An important security consideration is that the verifier must check that all components are valid before performing the verification equation. The public key P must be a valid point on the curve and not the point at infinity. The signature scalar S must be in the range 0 to n-1. The X coordinate Rx must represent a valid X coordinate of a point on the curve. If any of these checks fail, the signature must be rejected immediately without even attempting the verification equation. These checks protect against various malleability attacks and ensure that invalid signatures are rejected efficiently. Python implementation setup. Let's now transition to implementing Schnorr signatures in Python. We'll use the cryptography library, which provides high-quality implementations of elliptic curve operations, and the hashlab library for SHA-256 hashing. The cryptography library is well maintained, has undergone security audits, and provides a clean API for working with elliptic curves. While we could implement the low-level elliptic curve arithmetic ourselves, using a well-tested library significantly reduces the risk of implementation bugs that could compromise security. First, we need to install the cryptography library if it is not already available. We can do this using pip install cryptography. This library provides the elliptic curve class hierarchy and various backends for performing cryptographic operations. For our purposes, we will be working primarily with the SECP256K1 curve, which is available in the library. We will also need the EC module, which contains the elliptic curve cryptography functionality, and we will import specific classes like SECP256K1, which represents the curve parameters we discussed earlier. The structure of our implementation will consist of several functions. We'll have a function for key generation that creates a private key and derives the corresponding public key. We'll have a function for deterministic nonce generation following RFC 6979, which will use HMACDRBG to derive K from the private key and message. We'll implement the tagged hash function as specified in BIP 340, which will be used for challenge generation. We'll have a signing function that takes a private key and message and returns a signature. Finally, we'll have a verification function that takes a public key, message, and signature and returns true or false, indicating whether the signature is valid. When working with elliptic curve points in Python using the cryptography library, we need to be aware of the different representations. Points can be represented in affine coordinates with x and y values, or in various projective coordinate systems used internally for efficient computation. The library handles most of these details for us, but we need to know how to extract the x and y coordinates when needed, and how to construct a point from coordinates. We also need to handle the point at infinity specially, as it is the identity element of the elliptic curve group and represents the result of adding a point to its negation. For integer arithmetic modulo n, Python's built-in integer type can handle arbitrarily large integers. This makes it perfect for cryptographic applications. We will use the modular exponentiation operator, POW, with 3 arguments for efficient modular operations. For example, POW ABN computes a to the power of b modulo n efficiently, using binary exponentiation. For modular multiplicative inverses, which are needed in some operations, we can use POW-1n in Python 3.8 and later. This computes the inverse of a modulo n using the extended Euclidean algorithm. We will also need to convert between different representations, bytes, integers, and hex strings. Python provides convenient methods like integer.fromBytes, integer.toBytes, and the hex method for these conversions. Point lifting and coordinate recovery. One of the elegant optimizations in BIP 340 Schnorr signatures is the ability to transmit only the x-coordinate of the nonce point r, reducing the signature size from 96 bytes to 64 bytes. This optimization relies on a mathematical property of elliptic curves. For any valid x-coordinate on the curve, there are at most 2 corresponding y-coordinates, and these y-coordinates have opposite parity, meaning one is even and one is odd. The process of recovering the full point coordinates from just an x-coordinate is called point lifting or x-coordinate recovery. To understand point lifting, let us recall the SECP256K1 curve equation. Y squared equals x cubed plus 7, all modulo the field prime page given an x-coordinate. We can compute y squared by evaluating x cubed plus 7 modulo page if this value is a quadratic residue modulo p, meaning it has a square root, then there exists a valid point on the curve with this x-coordinate. To find the y-coordinate, we need to compute the modular square root of y squared modulo page for SECP256K1, where the prime p has the special form p equals 3 modulo 4. There is an efficient formula for computing square roots. Specifically, If y squared is a quadratic residue modulo p, then y equals plus or minus y squared raised to the power of p plus 1 divided by 4, all modulo p. The computation of the modular square root gives us two possible y values, y and negative y modulo p, which is the same as p minus y. These two values have opposite parity. One will be even and one will be odd. In BIP 340, we adopt the convention that the y-coordinate of R is always even. Therefore, during verification, when we need to recover R from its x-coordinate, we compute both possible y values and select the even one. This convention is what allows us to save 32 bytes in the signature, as the verifier can deterministically reconstruct the full point R knowing only that it has an even y-coordinate. Implementing point lifting requires careful handling of edge cases. First, we need to check that the x-coordinate represents a valid point on the curve, meaning that x cubed plus 7 modulo p is indeed a quadratic residue. If it is not, then there is no point on the curve with this x-coordinate, and the signature should be rejected as invalid. Second, we need to implement modular exponentiation efficiently, as computing y squared to the power of p plus 1, all divided by 4, involves working with very large numbers. Python's built-in POW function with 3 arguments handles this efficiently using binary exponentiation. Third, we need to determine the parity of the computed y value and potentially negate it to ensure we get the even solution. Complete signing implementation. Now let's implement the complete signing function that brings together all the components we have discussed. The signing function takes a private key represented as an integer and a message represented as a byte string, and it produces a 64-byte signature. The function needs to handle several critical steps, including deterministic nonce generation, point operations, challenge computation, and the final signature scalar calculation. Each of these steps must be implemented correctly to ensure both security and compatibility with the BIP 340 standard. The first step in our signing implementation is to ensure the private key is in the correct form. If the corresponding public key would have an odd y-coordinate, we need to negate the private key. This is part of the BIP 340 convention that ensures all public keys implicitly have even y-coordinates. To check this, we compute the public key point p equals d times g, extract its y-coordinate, and check if it is odd. If the y-coordinate is odd, we replace d with n minus d, which is equivalent to negating d modulo n. This negation also negates the point p, giving it an even y-coordinate. This step ensures consistency with the BIP 340 specification and allows for more compact public key representation. Next, we generate the nonce k using RFC 6979 deterministic generation. We hash the message using SHA 256 to get a 32-byte message digest. Then feed this along with the private key into our HMACDRBG-based nonce generation function. The deterministic nonce generation is crucial for security because it eliminates any dependence on a random number generator that might fail or be predictable. The nonce k must be in the range 1 to n-1. And our generation function ensures this by reducing modulo n and checking for 0. With k in hand, we compute the nonce point r equals k times g using elliptic curve scalar multiplication. The nonce point r also needs to have an even y-coordinate, according to BIP 340. We check the parity of r's y-coordinate. If it is odd, we negate k by computing n minus k. This negation flips the y-coordinate from odd to even while keeping the x-coordinate the same. We then compute the challenge e by calling our tagged hash function with the x-coordinate of r, the x-coordinate of the public key p, and the message. Finally, we compute the signature scalar s using the formula s equals k plus e times d, all modulo n. The signature we return consists of the x-coordinate of r as a 32-byte value and s as a 32-byte value, giving us our 64-byte Schnorr signature. This signature is deterministic for a given private key and message combination, making it reproducible and testable. Implementing complete verification. The verification function is the counterpart to signing and allows anyone with the public key to validate that a signature is authentic. The verifier receives the public key as an X coordinate representing a point with even Y coordinate, the message as a byte string, and the signature as 64 bytes consisting of R sub X and S. The verification function needs to reconstruct the nonce point R, recompute the challenge, and check the verification equation. If all checks pass, the signature is valid. If any check fails, we must reject the signature and return false. The first validation step is to check that all inputs are within valid ranges. The signature scalar S must be in the range 0 to n-1. If S is negative or greater than or equal to n, the signature is invalid and we return false immediately. The public key X coordinate must represent a valid point on the curve, meaning that when we attempt to lift it to a full point, the operation must succeed. The message can be any byte string, as it will be hashed during challenge generation. These preliminary checks prevent certain edge case attacks and ensure we're working with mathematically valid values. Next, we reconstruct the challenge E using the same tagged hash computation that was used during signing. We hash the X coordinate of R, which is given in the signature, the X coordinate of the public key, and the message, using the BIP340 challenge tag. This gives us the challenge value E modulo n. This challenge must match exactly what was computed during signing for the verification equation to hold. Any difference in the challenge computation, such as using a different hash function, tag, or input ordering, would cause valid signatures to fail verification. Now comes the core verification step where we check the Schnorr equation. We need to verify that S times G equals R plus E times P. We compute the left side by performing scalar multiplication of S with the generator point G for the right side. We first need to recover the full point R from its X coordinate using point lifting with the even Y coordinate. We then compute E times P through scalar multiplication of the challenge with the public key point. Finally, we add R and E times P using elliptic curve point addition. If the left side equals the right side, meaning both the X and Y coordinates match, then the signature is valid and we return true. If the points don't match, the signature is invalid and we return false. This verification equation is the mathematical heart of why Schnorr signatures work, as it cryptographically binds together the nonce, the challenge, the public key, and implicitly the private key through the relationship established during signing. Helper functions implementation. To build a complete Schnorr signature implementation, we need several helper functions that handle the low-level cryptographic operations. These helpers include functions for elliptic curve point operations, coordinate conversions, modular arithmetic, and hash computations. While many of these operations are available in cryptographic libraries, understanding how to implement them is valuable for debugging, optimization, and ensuring correctness. Let's walk through the key helper functions we need. The first essential helper is the tagged hash function specified in BIP340. This function takes a tag string and data bytes as input, and produces an SHA-256 hash with domain separation. The construction is tagged hash equals SHA-256 of the concatenation of two SHA-256 hashes of the tag, followed by the data. This double prefix with the tag hash ensures strong domain separation, preventing hash outputs from one context from being misinterpreted in another. In Python, we implement this using the hashlib library's SHA-256 function. We first compute and cache the tag hash. Then, for each tagged hash invocation, we create a new hash object, update it with the tag hash twice, update it with the data, and return the digest. Another crucial helper is the point lifting function that recovers a full elliptic curve point from just an X coordinate. This function computes y squared equals x cubed plus 7 modulo p, then computes the modular square root to find y. For the SECP-256K1 curve where p equals 3 modulo 4, we can compute the square root using the formula y equals y squared raised to the power of p plus 1 divided by 4, all modulo p. We then check the parity of y and select the even solution, as required by BIP 340. If no valid square root exists, meaning x doesn't correspond to a point on the curve, we raise an exception or return none to indicate failure. We also need conversion helpers for moving between different representations of cryptographic values. The int to bytes 32 function converts an integer to exactly 32 bytes in Big Endian format. This is the standard representation for SECP-256K1 field elements and scalars. The bytes to int function performs the reverse operation, converting 32 bytes back to an integer. These conversions are used extensively when serializing signatures and keys for transmission or storage, and also when deserializing them for cryptographic operations. Python's built-in int dot to bytes and int dot from bytes methods handle these conversions efficiently. For elliptic curve point operations, if we are using a library like the cryptography package, it provides methods for scalar multiplication and point addition. However, if we were implementing from scratch, we would need to implement the point doubling formula for computing 2 times p and the point addition formula for computing p plus q. These formulas involve modular arithmetic with the coordinates and are the fundamental operations that enable elliptic curve cryptography. For scalar multiplication n times p, we typically use the double and add algorithm, which processes the bits of n from most significant to least significant, doubling the accumulator for each bit and adding p when the bit is 1. This gives us logarithmic complexity in the size of n rather than linear complexity from naive repeated addition. Test vectors and validation. Testing cryptographic implementations is absolutely critical because even small bugs can lead to complete security failures. For Schnorr signatures, we need to verify that our implementation correctly handles the test vectors provided in the BIP 340 specification. Test vectors are predefined inputs with known correct outputs that allow us to verify our implementation matches the standard exactly. BIP 340 includes numerous test vectors covering normal cases, edge cases, and cases that should fail validation. The test vectors in BIP 340 include the private key as a 32-byte hex string, the corresponding public key x coordinate, a message to sign, and the expected signature. For each test vector, we should verify that our key generation produces the correct public key from the private key, that our signing function produces exactly the expected signature bytes when given the private key and message, and that our verification function returns true for the valid signature and false for modified signatures. If any of these checks fail, we have a bug in our implementation that must be fixed. Let's walk through testing with a specific example vector. Suppose we have a private key represented in hexadecimal. We convert this to an integer, then use our key generation function to derive the public key. We compare the public key x coordinate to the expected value in the test vector. Next, we take the message from the test vector, which might be a simple string like test message, and convert it to bytes. We call our sign function with the private key and message bytes, and we should get back a 64-byte signature. We convert this signature to hexadecimal and compare it character by character to the expected signature in the test vector. For BIP 340, because nonce generation is deterministic following RFC 6979, we should get exactly the same signature bytes every time. We should also test failure cases to ensure our verification function correctly rejects invalid signatures. For example, we can take a valid signature and modify 1 byte. We then verify that the verification returns false. We can also use the signature with a different message than it was created for and verify that it fails. Similarly, using the signature with a different public key should also result in a failure. It is also important to test edge cases, such as zero values, maximum values, and boundary conditions. Testing with the official BIP 340 test vectors ensures our implementation is compatible with other conforming implementations. This is essential for interoperability in systems like Bitcoin, where multiple implementations need to work together correctly. Security considerations. Implementing cryptographic protocols correctly requires attention to numerous security considerations beyond simply getting the mathematics right. For Schnorr signatures, several critical security properties must be maintained throughout the implementation. Let's discuss the most important security considerations that developers must keep in mind when implementing or using Schnorr signatures in production systems. The most critical security requirement is that nonces must never be reused with the same private key for different messages. If an attacker observes two signatures with the same nonce key but different messages, they can algebraically solve for the private key. Here's why. If we have two signatures, R, S1, and R, S2, for messages M1 and M2, both using the same key, then we know S1 equals K plus E1 times D, and S2 equals K plus E2 times D, where E1 and E2 are the challenges. Subtracting these equations gives S1 minus S2 equals E1 minus E2 times D. Since we know S1, S2, E1, and E2 from the public information, we can solve for D as S1 minus S2 times the modular inverse of E1 minus E2. This is why deterministic nonce generation following RFC 6979 is strongly recommended, as it completely eliminates the risk of nonce reuse. Another Schnorr versus ECDSA comparison. To appreciate the advantages of Schnorr signatures, it is valuable to compare them directly with ECDSA, which has been the dominant signature scheme in blockchain applications until recently. Both schemes are based on elliptic curve cryptography and provide similar security levels, but they differ significantly in their mathematical structure, implementation complexity, and advanced features. Understanding these differences helps explain why Schnorr signatures are gaining adoption in modern cryptographic systems. From a mathematical perspective, Schnorr signatures have a linear structure that ECDSA lacks. The Schnorr signing equation S equals K plus E times D is a simple linear combination of the nonce and private key, weighted by the challenge. This linearity enables signature aggregation, where multiple signatures on different messages by different signers can be combined into a single signature that's the same size as an individual signature. ECDSA signatures, in contrast, use a nonlinear equation where R is derived from the x-coordinate of K times G, and S equals K inverse times hash of message plus R times private key, modulo N. This nonlinear structure makes aggregation impossible and complicates security proofs. Security proofs are another area where Schnorr has a significant advantage. Schnorr signatures have a formal security proof showing that forging a signature is as hard as solving the discrete logarithm problem, assuming the hash function behaves as a random oracle. This proof is a reduction proof, meaning if you could forge Schnorr signatures, you could use that ability to solve discrete logarithms, which is believed to be hard. ECDSA, despite being widely used, lacks such a formal security proof. While ECDSA is believed to be secure and no practical attacks are known, the absence of a provable security reduction is a theoretical weakness. For applications requiring the highest assurance, provable security is an important consideration. Signature aggregation in MASIG. One of the most powerful features enabled by Schnorr signatures is signature aggregation, which allows multiple signatures to be combined into a single compact signature. This property stems directly from the linear structure of Schnorr signatures and has profound implications for blockchain scalability and privacy. The most prominent signature aggregation protocol for Schnorr signatures is MASIG-2, which enables multiple parties to jointly create a single signature without any trusted setup or interactive rounds during signing beyond the initial key aggregation phase. Practical applications in Bitcoin. Schnorr signatures were officially activated in Bitcoin through the Taproot upgrade in November 2021, marking one of the most significant protocol improvements since SegWit. The adoption of Schnorr signatures in Bitcoin, specified in BIP 340, brings numerous benefits for privacy, efficiency, and functionality. Understanding how Schnorr signatures are used in Bitcoin provides insight into the practical impact of this cryptographic primitive in real-world systems handling billions of dollars in value. The most immediate benefit of Schnorr signatures in Bitcoin is improved transaction efficiency. Before Taproot, multi-signature transactions required revealing all public keys and providing a signature from each required signer, resulting in transaction sizes that grew linearly with the number of participants. With Schnorr signatures and key aggregation, a 2 of 3 multisig or even a 15 of 15 multisig can be represented on-chain as a single public key and single signature, indistinguishable from a regular single signature transaction. This dramatically reduces transaction fees, which are proportional to transaction size in Bitcoin, and improves blockchain scalability by reducing the data that must be stored and transmitted by all nodes. Privacy is another major advantage of Schnorr signatures in Bitcoin. With ECDSA multi-signatures, blockchain observers could see exactly how many parties were involved in a transaction and what the signing threshold was. With Schnorr key aggregation, a complex multi-signature setup looks identical to a simple single-key transaction on the blockchain. This fungibility improvement makes it harder for chain analysis companies to track and discriminate between different types of transactions. Combined with Taproot's script tree structure, complex smart contracts can be executed privately, revealing only the path that was actually used rather than all possible execution paths. Conclusion and future directions. We've covered a comprehensive journey through Schnorr signatures, from the mathematical foundations through complete implementation details to practical applications. Schnorr signatures represent a significant advancement in digital signature technology, combining mathematical elegance with powerful practical properties. The simplicity of the signing equation S equals K plus E times D belies the sophisticated cryptographic engineering that makes the scheme secure, efficient, and versatile. The key takeaways from this presentation are that Schnorr signatures offer provable security through reduction to the discrete logarithm problem, something ECDSA cannot claim. They provide signature aggregation capabilities that enable multi-signature transactions to be represented compactly on blockchains. Looking to the future, Schnorr signatures will continue to gain adoption across cryptocurrency systems. We're already seeing implementations in Bitcoin through Taproot, and other blockchain platforms are evaluating adoption. For developers who implement Schnorr signatures, here are the most important recommendations. First, use well-tested cryptographic libraries, rather than implementing low-level operations yourself. Second, follow standards like BIP 340 for interoperability. Third, implement comprehensive testing, including official test vectors. Fourth, use deterministic nonce generation, following RFC 6979. And fifth, carefully consider side channel protections, especially if implementing for environments where attackers might have physical access. The cryptographic community has done extensive work to make Schnorr signatures secure and practical, but correct implementation still requires careful attention to detail. Thank you for your attendance. Please consider subscribing to the channel.